The other important ray optic effect, other than reflection, is something called refraction, and that's what we cover today. When a light ray moves from one transparent medium into another, its direction might change, a phenomenon called refraction. It will also reflect from the boundary, but usually more than 95% of the energy goes through. So we have an incident ray, it hits the surface that's here, some of it is reflected, you can see it very weakly, but some of it continues on, and yet if we were to draw the continuation of that ray, it would have, that's terrible. It would have gone this way, and we can see that it has moved a bit. It's changed direction. And then actually when that hits this ray, again, it would have normally gone like this, but it's moved again. It's bent again. All right, here we're getting double refraction because we have two surfaces. All right, here we sketch out a ray diagram for a bunch of parallel rays, and we see that they all refract off of a flat surface. They refract in parallel fashion. But if we have a point source, then of course they'll refract different angles because they're hitting at different angles. We'll usually focus on just one of the ray rather than all of them. This leads to something called Snell's law, which is an empirical relation, although there are theoretical underpinnings for it. It was discovered by people very carefully making measurements with light beams. And the relation is if we take the index of refraction of the first material times the sine of the angle at which it hits the surface, that will equal the index of refraction of the second material times the sine of this angle. And again, to use the sines, we have to use it from the normals. All right, from this thing, not from the surface, but from a line perpendicular to the surface. This is actually, in fact, how n was originally defined. This is where the idea of index refraction came from. Altogether, this is called something called Snell's law, named after, obviously, some person named Snell. One thing to note here is that the refracted ray is closer to the normal. In other words, I've drawn the dashed line as well. That's what would have happened if there had been no medium change. So the light would have traveled this way, and we can see that the ray has moved in the direction of the normal. It's bent towards the normal. Snell's law is completely symmetric. In other words, the N1 and N2 there were either index. I didn't say which one had to be the incident and which was reflected. By the way, this is something your textbook does right, but a lot of textbooks do wrong. So if you go on, you might see this differently. But they'll say N incident sine theta incident equals N reflected times sine theta reflected, which is certainly true, but implies that there's some sort of asymmetry there. Whereas really we're saying if we run a light beam back the other way, out of the N2 into the N1, it would follow the same paths. Light travel is essentially time reversible. If we have N1 more than N2, it turns out that we get to use the same equation, but in that case we can see that the refracted ray moves away from the normal. It swings outward instead of swinging inward. So qualitatively, the general rule is when entering a new medium, a ray of light swings towards the normal if the new index is greater and away from the normal if the new index is smaller. Remember that this has something to do that the index is related to the speed, but inversely. So if the new index is greater, then the wave is traveling slower, and so it gets kind of pulled towards the normal. And vice versa, if the new index is lower, then the speed is greater, it's freed up a little bit, and it can swing away from the normal. So, a laser beam moves through the air and falls on a plate of glass at an angle of 60 degrees to the normal. The index of refraction is 1.35. What is the angle of refraction to the nearest degree? So we go here and we say this is 60 degrees. And we'd like to know this. We simply set up Snell's law. N1 sine 1 is equal to N2 sine 2. And then we have 1, the index of refraction of air. And it's worth remembering at least that one. You don't have to remember any of the others, but you have to remember that 1 is the value for air. So 1 times sine of 60 degrees is 1.35 times sine of theta 2, which means sine of theta 2 is the inverse sine of 60 degrees over 1.35, which is 39.9 degrees, which to the nearest degree is 40 degrees. A laser beam moves through a plate of glass and reaches the edge at an angle of 40 degrees to the normal. The index of refraction for the glass is 1.35. What is the angle of refraction in the air to the nearest degree? So here we're given that this is 40 degrees, and we'd like to know what is that. Again, just some Snell's law. N1 sine theta 1 is N2 sine theta 2. So 1.35 sine 40 degrees is 1 sine theta 2. Sine theta 2 is the inverse sine of 1.35 sine 40 degrees, which is 60.20 degrees, which is 60 degrees to the nearest degree. Hey, something interesting happened here. It emerged from the parallel side at the same angle that it entered. It's almost as if the glass wasn't there. The ray doesn't bend by passing through the glass, it simply displaces some distance. As the thickness of the glass is reduced, the size of the displacement tends to zero. This will be important for lenses. The other thing that was important here is that these sides are parallel. It would have been different if there had been some sort of curve here, if for instance we had something like this. Then we might have gotten something very different. And we'll talk about that later, but those are more complex objects, and they'll take a little bit more analysis. All right. Based on this diagram, which statement is true? That N1 is less than N3, or that it's equal to N3, or that it's more than N3, or that we can't tell which one's less unless we know N2. Here we go back to Snell's law that N1 sine theta 1 is equal to N2 sine theta 2. That's what's happening at this junction. But we also have that N2 sine theta 2 is N3 sine theta 3. And that's what's happening at this junction. But transitive property in mathematics, since they're both the same thing there, we end up that N1 sine theta 1 is N3 sine theta 3. We can see that theta 1 is larger, so sine of theta 1 is larger, which means N1 must be smaller. We have that one. All right, a ray of light enters a layer of water at point X, passes through a layer of glass, exits through a layer of air at point Y as shown in the figure. Where would the ray exit if the layer of air if the glass had been replaced with a material of higher index of refraction? Notice that these are different indices, so this is not like before where things come out parallel because this is not water on both sides. All right, well, remember that this is the normal. If we had higher index of refraction, then it would have scattered even more towards the normal. And then when it went out here, it would be starting later and it would bend less, and so we'd end up over here, a point above Y. A light ray in medium 1 strikes a sphere of medium 2 with an angle of incidence theta as shown. I guess not really, above. The figure shows 5 possible subsequent paths for the light ray. Which path is possible if medium 1 is glass and medium 2 is air? Which is a little weird, so I'm going to shade in that this is a solid region of glass, and somehow inside of it we have sort of a spherical region of air, like a bubble that had been blown in the glass or something like that. That might make it easier to figure out what's happening on here. All right, well, I don't know what the index of the glass is, but we know the index of air is 1, and n is always 1 or more. So we have that N1, our glass, is more than N2. So that means at this junction, we're going from high index into low index, so the beam swings away from the normal. Well, this was the original direction. That's ray C, so C is already right out. And we know that we're going to swing away from the normal. Well, here's the normal, so it's going to swing away. So we're on path AB, right? That's our new path. Now it gets a little trickier because they haven't shown us everything. We need to find the normal to see what happens. We know that going from air back into glass, we're going from a low index into a higher index, so we're going to swing towards the normal, but we don't have the normal. Luckily, we do know that the normal is radial for a sphere. So that's the normal line, and we should swing towards the normal. Here is our continuation of our beam. That's what, if there had been no change. We need to move towards the normal. That's going to be this way. So the answer is A. It must go towards beam A. All right, consider a ray emerging from medium high index into one of lower index. Something interesting happens as we increase the angle of incidence. So we're going to start coming in almost perpendicularly, and then we're going to come more and more away from the normal and see what happens. All right, we get this. But then something weird happens. You see what happened there around 47 degrees? Let's watch it again. So you can see that eventually it looks like there is no refracted ray. The angle is becoming more and more, and we're at 40, 50, 60, 70, 80, 90, and 90, and then something weird happens. Does something like that happen in real life, or is this just a mathematical oddity? In fact, it does happen in life. Here's a demo. There's a piece of glass here. So you can see the reflection is almost mirror-like. What's going on? Consider if we solve for the angle of refraction. That is, we take Snell's law and we get sine theta 2 equals n1 over n2 times sine theta 1. Well, mathematically, it must be that sine of theta 2 is less than 1, or maybe equal to 1, but never bigger than 1. And we know that n1 over n2 is bigger than 1. So the thing on this side is already bigger than 1. We need to multiply it by something less than 1 to get the whole thing less than 1. Yet sine of theta 1 runs from 0 all the way to 1. So it will be some values such that the product exceeds 1. And in that case, there is no theta 2 that satisfies the equation. There is no angle at which the ray can pass into the air and still satisfy Snell's law. So it doesn't. It remains in the original medium completely reflected. This is called total internal reflection. By the way, this is one of those cases where when we say there is no theta 2, we mean there is no theta 2. Not that theta 2 is 0, not that it has no value, so it's 0. It's that it doesn't exist. The angle is undefined. There is no such angle that satisfies Snell's law. Here's a nice little picture of it as we increase the angle from coming in, and we can see that at shallow angles we go right perpendicular goes straight through. Shallow angles we get a little bit of refraction. But at the critical angle, we get reflection, and I guess we're a little less than the critical angle, so we get a little bit coming out. But at the critical angle, it would normally want to go along the surface here, and instead all of it gets reflected down. I find total internal reflection one of those very strange cases in physics where the mathematical necessity drives a physical reality. Sine of theta 2 can't be bigger than 1. So there can't be a transmitted ray. It just can't happen. The angle can't be defined. The underlying mathematics constructs the physical reality, which is kind of strange. We often abbreviate total internal reflection as TIR, and it occurs whenever the incident angle exceeds some critical angle theta c. We can find that angle by setting the last value for which sine of theta 2 is defined. Specifically, when theta 2 would be 90, meaning the ray doesn't enter the new medium, it kind of skirts along the edge. And we just set up Snell's law again. Sine of 90 is n1 over n2 sine of theta c. So theta c has to be the inverse sine of n2 over n1. Notice, of course, that theta c is not defined if n2 is more than n1. So when we're going into a higher medium, we never get TIR, only when the medium has a lower index. One of the applications of this is binoculars. We want large lenses, which means they have to be sort of separated out from your eye. And so we could use mirrors so as to see what's going on, but that would be finicky and fragile. Instead, most of them use some collection of prisms. This is an overly simplified version, but some collection of prisms that bounce the rays twice so as to get them in your eye. That also has the advantage of inverting and then re-inverting them so your things are looking upright as they should. One example is a light bulb is set in the bottom of a 3 meter deep swimming pool. What is the diameter of the circle inside which a duck swimming on the surface could see the bulb? So a place where the light ray from the bulb would reach the duck. The picture over here is to illustrate that if the duck were over here, I can't really draw ducks, but then no light ray from this can get out because the angle will always be more than the critical angle. But if we have the duck over here, then at least some rays can leave the bulb and reach the duck. Some nice, relatively basic trigonometry here. This distance is twice h tan c, because h tan c, tan theta c is going to be this radius, and of course we get twice it. And the critical angle for a water-air boundary would be the inverse sine of 1 over 1.33, which is about 48.7 degrees. And so the diameter of the circle would be 2 times the 3 meters times tan of 48.7 degrees, or about a diameter of about 6.8 meters. The same process in reverse leads to a limited field of view for someone under water, for instance. Anything whose rays would totally internally reflect would be seen, but things with a small angle can pass from above. So we can see this in reverse and say that the rays that can enter the eye of this swimmer, if they're coming from above, they'll come in and refract normally. But if we go out the other way, if we're at a high, rays that are coming at this angle must have been internally reflected from stuff outside. This leads to something called Snell's window, where from the bottom of a pool or something, you can see out over here, but down here we're seeing reflections of the bottom of the pool. One can use total internal reflection to construct a fiber that carries light, sometimes called a light pipe. By making sure the light always hits at an angle greater than the critical angle, we can make the light follow the glass. That's what's happening here. The light bounces and then bounces out again and keeps bouncing until eventually it leaves the perpendicular end. Commercial fibers are usually sheathed in what's called cladding, which is another type, a glass with higher index refraction than the inner glass, so that we can protect the inner glass. Usually this is the thing we're sending the light through, so rather than being an empty tube, we have some glass, so we have some higher index glass, and the light is bouncing, and then we can wrap this in plastic or whatever, and so we have it be protected. Here we have a picture of light propagating down a light pipe. To be entirely honest, this is actually not the method that people use, because abrupt changes in index of refraction lead to scattering of the light rays, dispersion of the light rays, because if there's any change in geometry, they go off at different angles. So actual fiber optic glass usually has its index change continuously, in other words, vary smoothly from 1.3 to 1.6. And you can show that that ends up changing the degree, bending the light ray smoothly. So if we have indices of refraction that are like this, where they're getting increasing amounts and we try and send a light ray through, when the light ray hits the first one, it will bend away from the normal, and then it will bend away from the normal again, and bend away from the normal again. And so you can make an almost sinusoidal variance, and it never really reaches the outsides. You don't have to worry about any transmission issues outside the core. All right, a student performs an experiment to determine the index of refraction of a plastic box. The student shines a laser beam from air, where any air equals 1, into a piece of plastic, where it has index n plastic, and an angle of incidence θ1, and measures the angular refraction θ2. Measurements are taken as θ1 is increased. From this data, the student produces the graphs shown. Which of the following is equal to the index of refraction of the plastic block? Question mark. Is it the slope of the best fit line in graph 1, or the slope of the best fit line in graph 2, or is it the inverse of the slope of the best fit line in each of those? Well, remember that we have that n1 sine θ1 equals n2 sine θ2. Of course, really we don't have an n1, or rather it's invisible because it's 1. So we have something like sine θ1 is n sine θ2. But our axis is that we have this on the x-axis, and we have sine θ2 on the y-axis. And so we have something like x equals ny. So I want to say that y is 1 over n times x. So 1 over the slope gives us that. So the inverse of the slope of the best line fit for graph 2. Why in terms of sines instead of theta? Because we want it to be linear. We always want to try and get our graphs to be linear. They're so much easier to analyze.